on Mars, and this is lab 4, talking about oscillations. The purpose of the lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. And the two main objectives were to compare the predicted motion and the observed motion, and then plot the energy charges that you compute in the model. For here, not unlike other labs, we're using VPython, a real-world spring and mass video, and then Excel and graphs to analyze our results. Some initial physics knowledge are the momentum principle, position update formula, period of oscillation, and conservation of energy formulas. The main result comparing the model to the experiment was that the experiment seems to go, the position of X seems to go up as time goes on, whereas the position of Y seems to go down as time goes on. And I'm going to talk a little bit why I think that is later in the video. So initial knowledge I came into the lab with is obviously Newton's second law, and then how it's derived for the code, nothing new, and then conservation of energy formulas. So kinetic energy, spring energy, the gravitational potential energy, and then the combined of the energy to get you the total energy. We'll also use the period of oscillation formula, which is T equals 2 pi over times the square root of m over k, is needed to calculate the spring constant, as well as use that formula to kind of estimate the T results in the results section. So the experiment and the computation, so the conditions, I used the lab video that was provided by Dr. Greco instead of doing my own. And that calibration length here was 7 meters from the origin to the mass. So in the system, we have our spring, our mass, and then the surroundings are Greco's hand, the earth, the air, etc. in that room temperature environment. Here, with this GIF on the right, you kind of see that the spring is oscillating in kind of an elliptical fashion. And then putting that video of Greco into Tracker, I found all of the values for X and Y position over time for the entire video. And then put those into Excel and then save as the CSV file to put into VPython. Some computation I did, some of these values I got from the video, some of them I got from the Tracker data, and just all of the computations and values I needed initially to start this lab. I took all of those values I either gathered or computed and began placing them into the code where needed. You can see from left to right here, as well as the force of gravity, the force of the spring, and then the net force, and then the momentum principle and that position update formula, as well as the conservation of energy formulas got inputted, all of those that I went through earlier. And now we can talk a little bit about the results of the lab. So the VPython simulation gave us 3 charts as its output, the change in energy over time, and then the change in the X and Y position over time, 2 separate graphs there. Some source of error could have been like human error in Tracker. It's a little bit hard to calculate exactly where the spring is. The video is a little blurry, etc., etc. And I'm also speculating that the camera angle of the video and that we could only view it from a certain angle has also kind of edited that data a bit. So what does it mean? Questions for the results. For your model system, is the energy principle satisfied? Justify your answer by discussing that energy plot. So let's go back to that change in energy versus time plot. It seems that the energy principle is satisfied from this graph that I'm looking at. So over the entire change of time, the value for each of the energies that we're calculating here seems to be the same at the beginning and the end for kinetic energy, potential energy, and potential gravity, and then the potential energy of the spring, as well as delta E. I can't tell exactly where those values are, but they seem to match up from beginning to end. So I would say that the conservation of energy principle is satisfied here. Okay, and the last question, using data you obtained in Tracker, make 2 separate estimates of the oscillation periods in the X direction and the Y direction. So it seemed that the period of oscillation in the X direction went a lot quicker than the period of oscillation, not a lot, but by 2 seconds quicker than the period of oscillation in the Y direction. I'm not exactly sure why that is. I think it could have something to do with the way that Greco released it or the camera angle, etc., etc. And that's all I have. Thank you for your time.